Stone bridges don't survive because stone is perfect. They survive because the shape is. Before cement, before concrete, before steel, the only thing holding a stone bridge together was compression. If the shape was wrong, it failed. If the shape was right, it didn't need glue. Natural stone varies in strength, and without cement, you can't average out weak spots the way Roman Pozzolana lime mortar helped later builders do. So the real miracle is control of forces, of thrust paths, and of construction steps done in the wrong order exactly once. Stay with this, and the bridge stops looking like a pile of rocks. It starts looking like a machine that only works when every piece is placed with intent. A stone bridge can lose the fight before the first stone shows up. It loses when the river keeps moving, keeps digging, and keeps undoing plans. This early stage isn't advanced math, it's field work. Builders need a place to stand, a place to mark, and a place to stack heavy stone where it won't slide away. They have no modern pumps to clear a hole in minutes. They have no cranes to drop a pier exactly on a spot. So the first job is basic and stubborn. Make the river stop behaving like a river, at least for a while. A calm bend can look friendly and still be a trap. Soft silt can hold your weight one day, then turn to slurry when it's stirred. Gravel can seem firm, but a faster current can scoop it out from under you like a hand pulling a tablecloth. Even worse, the water attacks the edges. It finds the small leak in a temporary wall, then widens it until the whole worksite becomes a drain. Storms make that problem unfair. One hard rise in water can wipe out stacked materials, pull apart timber bracing, and refill a pit that took days to dig. And because the work is slow, the river gets many chances to interfere. The builders don't just battle water, they battle time. So they build a temporary river first. Cofferdams and diversions come in as the quiet heroes. A cofferdam is a fenced pocket in the water, made from timber walls, planks, and frames that are braced against the push of the current. Workers pack clay and earth into gaps to slow leaks, then add stone and rubble as weight. The goal isn't perfection. The goal is dry enough for long enough to start laying a foundation that won't shift. Sometimes the answer is to steer the flow away from the work. A small channel gets cut, or a barrier gets set upstream to nudge water into a different path. In low water seasons, they take advantage of natural drops in flow, then rush to lock in the first courses before the river rises again. It's a scheduling game dressed up as construction. This is also where an invisible design choice shows up: where the piers land. People admire arches, but piers do the dirty work. Place a pier on ground that can wash out, and the whole bridge inherits that weakness. Place it where the flow hits hardest, and the river will carve a trench around it. Place it where the current spirals, and you invite scouring that eats the bed down deeper every year. Pier shape matters too, even without modern drawings. Builders give the upstream face a pointed or rounded nose so it splits the current rather than taking it like a flat wall. They watch how debris moves. They avoid spots where logs and brush collect, because a jam acts like a sail in floodwater and adds a sideways shove the stone never agreed to carry. The river doesn't just pass by, it pushes. Then come the foundation tactics, which often look like carpentry and quarry work more than masonry. In weak soils, builders drive timber piles down until they reach firmer layers, then cap them so the load spreads across a larger platform. In mixed ground, they lay a rubble raft, a thick bed of stones that behaves like a crude slab, helping the pier sit without punching into the mud. Where the bedrock sits close, they key heavy stone footings into it, cutting and fitting so the base can't skate sideways. None of this is glamorous. It's also where small errors become permanent. If one pier settles even a little more than its neighbor, the arch above stops sharing load evenly. Stones that should stay squeezed together start to open at joints. Cracks follow the stress path like a signature. And this is the strange part. After all that work, after the riverbed finally feels quiet, the bridge still can't stand. An arch only works when it's whole. Half an arch is not half as strong. It's unstable, and it needs help just to exist while it's being made. So the first victory isn't an arch rising from the water. The first victory is a dry pocket, a locked base, and ground that agrees to hold still. With the site tamed, the next enemy is the empty air. A span has to exist before it exists. Now the work moves from riverbed to open air. Stone can't hang there on faith. An arch acts like a simple machine, but it can't start itself. Until the last stone goes in, gravity keeps asking questions. So builders gave the stone arch a temporary twin. They called it centering, a full timber frame shaped to the exact curve. It worked like a mold and a support at the same time, holding each piece where it needed to rest until the arch could hold itself. This is the part most people never notice because it's meant to disappear. The centering looked like a wooden bridge under the real bridge. Posts stood in the river worksite, beams carried the load, and curved ribs traced the future arch lines so each stone had a seat. The process is one way. If workers set stones on weak centering, the stones shift. If they strike the centering too soon, the arch can unzip, with wedges sliding and gaps opening in a chain. And if they lower it unevenly, one side starts carrying load first, the kind of lopsided pressure that turns hairline cracks into loud ones. Striking had to feel controlled, almost ceremonial. Builders lowered the support in small steps, keeping the release even across the span. They watched for movement, listened for grinding, and checked joints as the wood stopped doing the job and the stone took over. But before any of that, they had to get the curve right. No calculators, no printed plans. They used physical geometry that you can hold in your hands. A chord fixed at one point can mark a clean radius. A simple template can repeat the same curve again and again. And on tracing floors, full-size layouts drawn on a flat surface, builders could set out the arch shape at real scale, then carry those marks back to the work so both sides matched. That matching matters because the arch is a chain of wedges. Each voussoir is cut like a tapered block, wider at one face and narrower at the other. As you set them along the curve, they lean into each other, waiting for the final wedge that stops the motion. That last wedge is the keystone. It doesn't just fill a gap, it locks the ring so the stones press together instead of slipping down the ribs. After the keystone seats, the arch stops behaving like stacked blocks and starts behaving like a single compressed band. If you like engineering broken down like this, subscribe. Then builders add what looks like extra weight because it is. Spandrels, those side walls above the arch ring, hold back the fill. The fill itself packs the space above the curve and under the roadway. That dead load seems counterintuitive, but it helps keep the arch in compression, which is where stone behaves best. The real test, though, isn't whether the curve looks smooth. It's whether the forces travel safely through it. This is where thrust paths come in. Loads from the road and the masonry above don't fall straight down. They push along a path through the arch ring toward the supports. That line of thrust has to stay inside the stone because stone handles squeezing well but resists pulling badly. If the thrust line drifts too close to an edge, the arch begins to act like it has joints. A hinge forms. The stones start to rotate rather than press flat. Cracks open where you want tight contact, and the arch begins to spread. A grounded way to think about it is stacking books into a leaning curve. If your hands keep pressure centered, the stack can hold. But if the pressure slides toward the outside, the books twist, then slip. Then the whole curve fails from one small loss of control. Builders didn't run modern calculations, but they worked with rules that punished mistakes fast. They built centering stiff enough to keep the shape. They placed voussoirs so joints met cleanly. They kept symmetry because a small mismatch turns into a sideways shove at the supports. When thrust paths behave, the arch squeezes itself tighter as it works. When they don't, failure isn't mysterious. The thrust line exits the masonry, rotation starts, cracks spread, and the piers feel a growing push they were never sized to resist. That is the moment the bridge stops acting like a structure and starts acting like a slow, heavy lever. And now comes the twist. Sometimes stone and geometry still needed a helper. And the Romans in particular had a very specific kind of binder waiting in the wings. Stone by itself is honest, but it's not forgiving. Without cement, every joint becomes a small argument about contact. Natural stone arrives with quirks. One block is tough and tight. Another has hidden seams, or a rough face that only meets its neighbor on a few high points. If builders dry stack that work, those high points take the stress, and the weak spots get loud fast. Tiny gaps become tiny levers, and the arch starts to behave like it has too many moving parts. So builders had two ways to calm that problem down. They could cut and fit stone until it met cleanly, then accept that the joint still wasn't perfect. Or they could add mortar, a bedding that helped the load spread across the whole face instead of just a few ridges. Many crews leaned on lime mortar, which works well when you can keep things reasonably dry while it sets. It helps with seating stones, it fills small voids, and it limits small shifts that grow into cracks. But river work refuses to stay dry, and lime mortar has limits when joints stay wet. That's where the Roman approach stands out in the record. Romans used a pozzolana lime mix made from volcanic ash, lime, water, and sand, and it earned a special advantage. It could set and gain strength in damp conditions, even underwater. For bridge builders, that meant the joints and foundations and piers didn't have to wait for perfect weather. The binder could harden while the river did what rivers do. The real change wasn't magic glue. It was steadier contact. A good binder turns the joint into a working surface. Instead of stone-to-stone pressure landing on a few lucky points, the mortar helps carry the load across more of the interface. That reduces the lottery of imperfect cutting and mixed stone quality. It also keeps water from working into gaps that can freeze, loosen, and pry stones apart over time. And pozzolana mattered most in the spots that stayed damp forever. River piers live in a constant cycle of wetting and drying, with water pushing grit into joints and currents probing for weak seams. A mortar that keeps hardening in those conditions gives the pier a tighter skin and a stronger core, which is exactly where a bridge wants reliability. It helps to think of it like stage scenery. Two boards can lean together and stand, but one bump moves them. Add a thin layer of set material between them, and the contact stops depending on a perfect touch. The structure stops being a stack of hopeful matches and starts acting like a single piece. After the Roman period, that particular edge thinned out in many places. With less access to pozzolana-based practice, builders leaned harder on what they could always control: shape, thickness, and mass. They built with more stone, broader piers, and abutments that looked almost stubborn in their size, because weight can substitute for chemistry when you need stability and you can't trust the joints to behave. Later builders also adopted flatter profiles like elliptical, basket-handled arches, shaping the curve so it rises more gently while still controlling how forces travel. Those forms depend on careful layout and strong supports, because a low arch can increase sideways push if the rest of the system isn't ready for it. Next time you pass an old stone arch, read it like an exhibit. Look for where the river was made to behave, where centering once stood, and where the thrust is being caught. That's it for today. Click on the video to watch the next one.